Good
morning.
Good morning, Professor.
Good morning.
Good morning.
Oh, hey, good morning, Professor.
Good morning.
Anna, we can start with the presentation of the members and share their presentation.
Excellent.
Okay, thank you.
You're welcome. Good morning, everybody. Welcome to the Energy Symposium on Energy Security. This session will be about a specific way to achieve energy security. That is working on the efficiency on the demand side mainly, and the introduction of renewables. We will have 4 presentations and I would say 4 case studies that span from China, Japan, and Italy. So we are going to see whether the experience that our speakers are going to relate with may also suggest some benchmark in order to achieve energy security. So we will start by the presentation of Siqi Meng. Siqi is a PhD student at the School of Economic and Management of the China University of Petroleum. So I'll leave you the floor to your presentation. And so we have 4 presentations, and therefore the speakers are going to talk more or less 22 minutes. And I think that they will be able also to answer questions, if any.
Okay, thank you, Professor. Can every expert see my PowerPoint? I will start now.
It's okay.
Oh, it's okay. Good morning, all experts and scholars. I'm Siqi Meng, a PhD candidate from China University of Petroleum, Beijing. It's my great honor to participate in this academic conference. The title of my report is How Does the Provincial Renewable Energy Demand Evolve Under Multiple Influence Factors? An empirical study based on Chinese data. And my co-author is Professor Ren Jinsun. The report will be carried out in the following 4 aspects. First of all is the introduction of the author. I'm Siqi Meng, studying in China University of Petroleum, Beijing. Research interest focuses on energy and environmental economics, renewable energy electricity market, low carbon economy, and I have published 8 academic papers. My co-author, Professor Ren Jinsun, is my tutor. Because of time, I won't go into details here. Please just take a look. And the second aspect is that the article may form some highlights. Firstly, China's renewable energy demand presents obvious spatial spillover effect and present spatial positive correlation distribution. Secondly, the renewable energy policy has a positive effect on promoting the demand for renewable energy, and we expand the research from the perspective of time and space. Thirdly, green policies and innovations in the eastern and central China can significantly stimulate the demand for renewable energy. Firstly, about 30% of the impact of renewable energy policy on the demand for renewable energy is indirectly realized through green innovation. The research content, method, and the results of the article will be introduced in the following section. We first analyze the existing literatures and found out that first, few scholars studied on promoting mechanism of renewable energy consumption. Less attention is paid to provincial data and to sub-regional results. And the last one is existing literatures really analyze the decomposition of the time. The article has expanded the research on this aspect. The articles expand the third-party model and through spatial measurement method. After analyzing the spatial spillover effect of renewable energy consumption using the marine and green indexes, this paper conducts a national and sub-regional perspective spatial effect analysis based on provincial panel data. After the time effect decomposition, the research is conducted based on mesomeric effect model. This paper focuses on the impact of renewable energy policy support level and the green technology innovation level on renewable energy consumption, and slides population, industrial structure upgrading, foreign direct investment, and energy efficiency data as control variables. The main variables and the data sources are involved in the article are shown in the table. Before conducting specific research, we first carry out a core integration test. Next, we select the geographical proximity weight matrix for empirical study. In order to verify the spatial spillover effect of renewable energy consumption, we use the marine and green index to analyze it. Results shows that the distribution of provincial RE index in Chinese cities shows the spatial positive correlation distribution characteristic of high and low agglomeration. The scatter plot of marine and green indexes in the representative years can also prove the above conclusions. Next is the model selection. Combining the results of LM, RLM, and Haussmann test, the spatial fixed effect SAR model is selected. The analysis of SAR model results and the matrix shows that from the national perspective, renewable energy policy, GDP, in industrial structure upgrading, energy efficiency, and the technological innovation improvement and the reduction of fossil energy consumption will all promote the increase of renewable energy consumption. The following figures reflect the changes in renewable energy consumption in the Eastern, Central, and Western China over past 10 years. The last one is the changes in renewable energy policies in 30 provinces of China. It can be seen that different regions have their own characteristic and need to be studied in different regions. This paper takes the Eastern region as a benchmark, set to dummy variables in Central region and the Western region. The spatial aerial coefficients are significant in both Eastern and Central regions. This may be because the economic and the demographic conditions. And the policy support focused on these two regions too. Although the Western region has rich renewable energy results, its preference for renewable energy and its technology level need to be further improved. So there may be some lag in policy response. Next, we take the dynamic effect decomposition. The direct effect, spillover effect, and the total effect coefficient of renewable energy consumption are highly significantly positive, and the absolute value of coefficient generally increases over time. Finally, the result of mesomeric effect analysis shows that 13% of the positive promotion of renewable energy policy on consumption is indirectly realized through technological innovation. In this paper, the replacement matrix is selected as the comprehensive weight matrix of geographical economy to verify the robustness of the results, which I won't go into details here. Finally, I will focus on the conclusion and the limitations of the article. By expanding the stir-pipe model, this paper studies the evolution characteristic of renewable energy demand in certain provinces of China and the various influence factors. The empirical result shows that, firstly, China's renewable energy demand presents obvious spatial spillover effect and present a spatial positive correlation distribution characteristic of high and low type agglomeration. The renewable energy policy has a positive effect on promoting the demand for renewable energy by dynamic effect decomposition. The promotion effect on demand as a whole has increasing trend. Among them, 2016 to 2019 shows a significant upward trend. There are certain regional differences in the impact of basic variables represented by renewable energy policy and green innovation on renewable energy consumption. Green policies and innovations in the eastern and central China can significantly stimulate the demand for renewable energy, and the central region has a stronger driving effect. About 30% of the impact of renewable energy policy on the demand for renewable energy is indirectly realized through green innovation. Besides the functional and practical applications, the study has some limitations. The influence factor of RE index need to be further researched, and ninth, this paper only selects the number of green patents to represent the level of technological innovation, which is one of the limitations of the paper. And the next one is in the regional study of Chinese mainland. This paper is only divided into 3 regions, which can be further studied, and we will expand this aspect in the following research. That's all for my report. Thank you for your listening. Please comment and correct me. Thank you so much.
Thank you, Siqi. May I ask you just a question to clarify your results? What does it mean in economic terms, the pattern that you describe as high, low aggregation?
Okay. Thank you, Professor. Thank you for your asking. I used the Murray and Green Index to study it, and when the Murray's R index of the provincial CP, provincial R index is greater than 0, and Green C index is less than 1, and both are significant at the 1% level, which indicates that the distribution of China's renewable energy index is spatial positive correlation of high and low agglomeration. I don't know if I can understand. I can answer it well.
Yes, in the sense that your model, I mean, as I understand, the specificity is to have these spatial effects. So you have both this idea of spatial effect and spillover effects. And I was wondering, in economic terms, what does it mean? It means that a specific location of the renewable energy plants is determining an effect in terms of either there is more and more location, or there is of renewable plants, or there is at the contrary, zones that are not interested in terms of locating renewable energy plants. I was wondering if this is the interpretation that we have to give.
Sorry, I can't understand you well.
No, I just was wondering in terms of how we can summarize in economic terms, just what you do suggest in terms of, for instance, optimal location of, I don't know, of a solar plant, of a wind plant. Which are the regions that are the most interesting?
Regions. I don't know if I understand you well, but I think the technological innovation is a key factors, and we should improve the technological innovations in Western region to improve the whole Chinese renewable energy consumption, because the Central and Eastern Chinese renewable energy consumption is developed well, but the Western region need to be improved. Thank you.
Okay, so yeah, thanks. This is one of the questions that exactly I was, trying to understand what is the spatial pattern of location of renewable energy. Thank you very much for explaining your model and your results. Let me check if there are questions. I don't see them. So thank you. So we can move to the second speaker.
Okay, thank you.
So Nicola Sorrentino.
Okay.
Nicola is
good morning, everyone.
Good morning. At the Università della Calabria, and he's going to speak about our own country. Or is yours?
Thank you, Mrs. Chairman. Well, I'll present some studies we have developed in the context of the European project, which concern energy efficiency, new energy efficiency contract that we call it as a pay for performance. And so we only present some results regarding this project. And in particular, we focus the attention on the impact that may have an energy efficiency intervention on the power system. In particular, as you can see in the title, we investigate the interaction that can be that take place between energy efficiency at the building level, demand response that is available by the user to the power system, and the impact of the energy efficiency in the reliability of the power system. So, okay. So, as well known, there is a strong interest at the worldwide level to reduce the electricity, the energy consumption, with particular emphasis in substituting fossil fuel with electrical energy, so called electrification, and then use renewable sources to feed such kind of new devices, and so also to reduce the need of gas, mainly of gas, and so the methane, and in the final use, especially for at the residential levels. As we need to speed up this process, we have, in order to do that, we need to have much money to be used to implement such intervention, and so we need to become this intervention more reliable from the financial point of view. So we need to monetize any kind of improvement or value that may have an energy efficiency intervention, and in particular from the power system point of view, and that can become a value for the final user. So as I just said, we want to evaluate. We have developed a tool in order to estimate the possible impact of energy efficiency intervention in terms of an environmental sphere, so classical CO2 reduction, but also in terms of quantity of demand response that can be performed by the final user to the power system, if the power system asks for such kind of service, and also how this kind of the energy efficiency intervention may improve or reduce the impact of the load on the power system, so in the electrical system, system reliability. So we consider this method as to use some obviously input data, and mainly from the power system point of view, we need the national average fuel mix. That means how the electricity is produced hour by hour in the power system, the number and which type of peak critical hours present in the power system. That is a signal of the possible problem for power system reliability, and also historically the data, the needs of demand response request by the power system. To perform such analysis and so to evaluate the behavior and so the value of this kind of performance of energy efficiency intervention, we need to use to evaluate hourly data. So the basic idea is obviously to forget an approach in which energy efficiency is evaluated by an annual or a long-term evaluation, but mainly we want to know how this kind of energy efficiency intervention may impact on the load profile, okay, but hour by hour, because this is very important to evaluate the real value of energy efficiency. So we use as input a basic hourly profile. So that is in our procedure we use, that is the load profile before an energy efficiency intervention. Then I'm assured or estimated hourly profile in consequence of an energy efficiency intervention of a period that can be a day or some months or a whole year, okay? Then, with reference to such profile, we are able to evaluate the we consider the hour, the critical hour present in that the power system operator publish each year, in which there is most critical from the power system point of view. Then, for each hour, we have historically the mix we have in hour by hour in a whole year, and then the historical request of demand response, hour by hour, in the period we have considered, and obviously in the power system we have considered. Just Anna says we focus on the Italian case, so we have then we'll show the results we have obtained using Italian case. So considering using this tool we have developed, we are able to classify an energy efficiency intervention in terms of reduction in terms of CO2 emission, in variation quantity of energy that will be able for the final user to offer to the power system, and the reduction of quantity of energy requested by the user in the critical hours. So we have these three indexes in which we are able to evaluate the performance of the energy efficiency intervention. Obviously, the procedure, I skip how it is calculated because it is not so complicated. This is just a calculation spreadsheet, but it is interesting to evaluate in some realistic cases the results we have obtained. Well, we have monitored some real user located in south part of Italy. We have considered a certain number, obviously, of users. So we have hourly data from January to August 2020. And we have considered as this user will be aggregated using a similar profile, obviously, replicated such a profile, aggregated in order to reach a capacity in order to participate in a DR program in Italian system operator Terra that is called UVEM. So we are able, we wish to offer regulating capacity of 1 megawatt to the power system. So we have compared the three cases. We have used the model we have just outlined to compare mainly two interventions. The first intervention is an electrification intervention, in which we substitute a gas boiler with a heat pump. While the second intervention we are considered is an energy efficiency intervention, which we use in a combination of heat pump and thermal insulation. So if we look at the results in terms of these three these three index, we can note some important results. First of all, in terms of demand response, in the basic profile, you can see there is two numbers: number of success and number of failures. What does it mean? If an aggregation participates to a demand response program, they have to guarantee that 1 megawatt, as I say before, can be cut. Okay, if I will cut this power, I will be remunerated. If this power is not is not cut because there is no power, for example, in that hour requested by the final by the TSO, this is a failure. Okay, so I cannot perform what is requested by the contracts, and there are penalties on that. So if we look to the results in the three cases, basic profile, HP profile, and heat pump with the thermal insulation profile, we can see the number of success, the number of success, that is a positive value to the request by the transmission system operator increase. Okay, so we may have more gain from a final user that participate in a demand response program using after an energy efficiency intervention. Moreover, we are also able to evaluate the reduction of CO2. Okay, we have calculated the CO2 emission using a boiler gas, and when we use a heat pump, we have a very interesting reduction in terms of CO2, but also obviously with a further reduction of CO2 emission if we use thermal insulation of the building. Moreover, what has happened in terms of reliability? Obviously, when we introduce heat pump, there is an increase in the load power. So there are, as you can see, an increase of 442 increase of power in critical hours. So there is a negative effect on the power system reliability of the energy efficiency intervention. But if we, besides the heat pump intervention, we use a thermal insulation, this number of critical hours in which we have an increase of power is reduced. So this is a further benefit for in introducing thermal insulation when we have when we use heat pump. We have a reduction in terms of impact in the power system reliability. Just here some more results in order to show what happened. As you can look at the figure in the on my left, the upper one is a failure, okay, performance failure, in which we have not enough power that can be cut. On the lower value, in the lower figure, we can see there is a cut of energy, possible cut of energy requested by the transmission system operator as the power is increased in the hour in which it is requested. Moreover, on the slide, in the picture on my right, it is represented the number of failures we have in the basic profile and using the heat pump and thermal insulation energy efficiency intervention. As it is more or less clear that when we have energy efficient intervention, there is no failure in this case, and for the period we have considered, respect to the basic case, to the when the power system operator requests the service. This is just a more clear representation of the figure we have just discussed. In terms of CO2, this I have reported just a simple representation of the CO2 calculation in hourly base, just to show how obviously it's a kilowatt hour reduction or increase in 1 hour is not the same if it is performed, for instance, in the evening or in the daytime, as obviously we have an high impact in the fuel mix of renewables and in particular of solar panels. So the content of the kilowatt hour saved in the evening is the content of CO2 is higher than in the day during the day hour during the day. Okay, so we have when it is important not only to reduce the energy, but at what time we reduce energy in order to reduce CO2 emission. So it's better to reduce energy in the evening hour. Okay. We have calculated the reduction, taking into account this consideration, and the value is here reported. Then here just reported a figure in which we report the quantity of energy in the critical hours. Obviously, when we use heat pumps to substitute obviously gas boiler, there is an increase of power in the critical hours. But as we can see, by using thermal insulation in combination with an heat pump, this impact is reduced, both in terms of load, of number of hours in which there is an increase, but also in terms of total load increase in critical hours. After this presentation of this study, what can we say? That we may measure an energy efficiency intervention in terms of some benefits or reduced impacts that is behind the classical CO2 emission reduction. Is not only the benefit on that. For the user, there is a more demand response availability that can be used to obtain income and improve the operation of the power system, and moreover is able to help again the transmission system operator in assuring the electric system operation. And the idea is for such services and for such benefit, we may have a gain, and so to improve the return on investment of the energy efficiency intervention. This is possible only if we consider the performance and evaluate the performance of the energy efficiency on an hourly basis, obviously. So we have to have a monitoring system in which we are able to monitor the real performance of building of a user after the energy efficiency intervention. So this is the concept that is behind the pay for performance contract that just I say is basically in the focus of the Sensei project, that is an H2020 project approved by the SINEA. And we have developed, obviously we are at the end of the project. We have a lot of application on that and the dissemination materials. If someone is interested, we will have our final conference in Brussels. This is the date. We also will be performed. We can join by in remote mode, and if we want to have a full interaction with Sensei partners and to understand more deeply what is a pay for performance contract, we may join to our community. Okay, thank you very much to everyone to your attention.
Thank you very much for your presentation and also for sharing the information about this interesting program. I just wanted to understand, so the idea is that the consumers will be, the consumption profile will be measured through a smart meter, I guess.
Yes.
And you also optimize the price that has to be paid in order to adjust. So something that I didn't catch is how the prices varies in order to enforce the optimal profile.
Yeah, there is an optimization in this case. We have just check, okay, check after a performance of the final user. What is the benefit? Obviously, this the behavior may be optimized, okay. So you can try to modify the load profile hourly by an optimization model. So change this, here is reported as measured hourly profile. How is performed this hourly profile is the key point, okay? So you have looking at this indicator, you can optimize the behavior, okay? And so to optimize the load profile. In this case, we have an optimization. We only check, evaluate.
But here you deal with the quantity. So you mean that as the dual of your optimization is able to tell also which is the pricing profile that has to be applied to every consumer involved in the
yes.
program?
Yes. So we, in function of the, I have skipped the price that can be applied in this case because it is more complicated to evaluate. But obviously there is a price, okay? A price that can be used and that can be applied to each variation quantity, and so to transform this in money.
Because this is, I think, well, one of the most difficult question in implementing such kind of incentives. So to convince consumers that it pays to make some intervention in or renovation that here is, let's say, minimal, in the sense that they only have to change the heating system. But we know that there is a lot of inertia in consumers' behavior. So that is why I was wondering what we can learn about the price trajectory that is also associated to the change in the load profile.
Yes, I completely agree. This is the problem of the pricing is very important. Is also to involve the users in such process is not easy. Is the most difficult target, I think. From a technological point of view, probably we have no problem. There are problem on the regulatory point of view, but also when we talk with the regulators, there is some interest and some understand that can be a possible way to implement it, to enforce the building renovation by a pay for performance. For the user is a very is much difficult.
So what you propose is to replace the subsidies with such a pay per performance schemes. So instead of subsidizing the installation of a heat pump, as it is mostly the case today, but no one makes it.
Yes. It's not only we have the case of the heat pump, but we may use any other kind of intervention. So they simulate because the problem we think that has to be completely avoided, that we may use energy efficiency as a fit and forget intervention. Okay, we have a thermal insulation. It's okay. I will pay for the thermal insulation. For heat pump, okay, I give you. But if there is no correct use of this kind of intervention, we may not have the real effect on the system, and so and for the user, obviously, okay, in the same time. So we have to stimulate to have an interactive and active participation also in the energy efficiency intervention by the final user. And to get money from that.
Yes.
Okay. Because if
that's the key point.
That is the key point. Okay, you may have you can get money, and if you get money, you can return on investment and so on, and you reduce your the gas and the cost and the electricity cost, etc., etc. So, but we have to involve people otherwise and pay for that. Otherwise, it's quite difficult. This is the concept behind the pay for performance contract.
Thank you very much. Thank you, Nicola. So we are going to move to the third speaker. So Jan.
Oh, hi. So I will show my. Okay.
Yeah. PhD student at the Kyoto University.
Thank you. Can you see my PowerPoint?
Yeah.
Oh, okay. So I'm so pleasure to attend this conference, and my name is Chuyue, and just
put it in full screen mode. Yeah.
Oh.
Excellent.
Thank you. I will start my presentation. My presentation is potential reduction projection of residential energy consumption and analysis of local economic impact with a perspective on traditional timber house in Japan, a case study of Kyoto City. Okay. And I will explain this research as 6 parts. And the first part is the research background. I will explain the energy situation in Japan's supply side. And we can see this picture that Japan self-sufficiency is at 2019 is just 12.1%. And Japan is about 20% depend on the Middle East region for coal oil, and LNG and coal. Japan relies on imports from other countries, including Asia. And at 2010, and the nuclear power is share is 11.2%, but at 2019 is just 3%. So the fossil force has increased, has been 84.8%. And next is energy situation in Japan, and Kyoto City is the bind side. We can see these 2 pictures is final energy consumption percentage by sector. We know that in 2022, the national and the Kyoto City residential energy consumption rates are 16% and 25%, and Kyoto City is above the national average. We know that energy sector can made a lot of greenhouse gas emission. So Japan planned a warming countermeasure plan. We know that all sector must reduce the greenhouse gas 46% until 2030. Especially resident sector must achieve 66%, which is a high level of regulation. And now we can see the Japan's house installation performance and building energy saving measures. We can see this picture that expect Hokkaido, Japan's house installation performance, it has a low quality, which is lower than other country. And now the new installation standard is just 11% to share. Japan's building energy saving law become into force just at 2021. So in the view of the above background, in order to resolve Japan's tight energy supply and demand sector and achieve the goals of the Japan warming countermeasure plan, so strengthening energy conservation measures for homes and buildings is an urgent issue. So I have 3 research questions. One is what is the potential for reducing energy consumption and CO2 emissions after improving the thermal installation performance of Japanese house? 2 is Kyoto City, and we know is an Asian capital, has left behind many traditional wooden house. So do traditional wooden house consume more energy than ordinary house? The third one is what changes can be made to the local economy by improving the installation performance? And my study area is Kyoto City. We can know these 2 pictures from Google Earth. The Kyoto City is a travel and Asian capital. So because according to landscape law, Kyoto City cannot have a high building like Tokyo City, and at the center of the city, a lot of traditional wooden house have a lot of traditional temple house. The population of this Kyoto City, we know this picture that the percentage of 1 person household reach 48%, and 30% is elderly single person. 2 person household account for 23% of all household, of which 10% has both members who are elderly. This Kyoto City's residential housing situation, we can see this 4 picture. We know that detached house is mostly made from wooden and have 2 floors, and apartment house mostly made from no wooden. And before 1915 and 1951 to 1970, a lot of traditional temple house we have a lot of traditional temple house. So the Kyoto City's traditional temple house we call is Kyomachiya. Kyomachiya is look like this picture, and it has a long street and have a every Kyomachiya have street garden. But most of the extinct Kyomachiya were built after the Meiji period. Is from 1868 to 1912. So before this, I will explain my research method. My research method mostly is bottom up measures. Bottom up is grouping a large number of buildings into several building phototypes with common energy consumption patterns, which can be struck to calculate the overall building energy consumption. I made Kyoto family housing model to zero energy housing and apartment house, detached house, and Kyomachiya, and put it into design builder to calculate the annual energy consumption. The simulation procedure for each household is like this follow. We put this building master's data and occupancy rate data for each room, and application and lighting utilization data for each room, and air condition schedule data and solar panel data into design builder. in the end, the annual energy consumption for each household and the PV generation, we can get this result. Now I will show that Kyomachiya's follow plan, and I built it in the design builder. This is his 3D model, and this is the detached house. The next one is apartment house. The simulation condition settings is shown as this picture, this table. According to Japanese insulation performance history, I made 4 types of insulation performance, and house type I also made 8 types to calculate. Each room's cooling heating source is all household use air conditioner, and the setting of the heating source. The detached house I made 4 types. This kotatsu is a special Japanese heating application. And water heater settings is also have three pattern to simulation each house annual energy consumption. The next is my research result, and these 2 group is from design builder's result. And we can see that Kyomachiya is traditional timber house, no insulation, and a detached house, no insulation. The traditional wooden house consume more energy than normal house, especially in heating and cooling. And we can and now explain the detached house, no insulation, and their energy house. Their energy house energy consumption is lower than detached room, no insulation, but their energy house has PV generation. So when all solar power generation is supplied to household energy consumption, can generate supplies of energy, electricity. And with the improved insulation performance, the energy consumption of cooling can be reduced by an average of 4 gigajoule per household. The end of the simulation, and I will set 4 scenarios to estimate the whole Kyoto City's family energy consumption. First scenario is the BAU with in Kyoto City not include Kyomachiya and PV. This scenario is Kyomachiya will be used as normal wooden, no insulation detached house, and all dwelling not have PV insulation. And scenario 2 is BAU in Kyoto City include Kyomachiya and PV. This scenario, among detached house, 30,000 houses are Kyomachiya, and amount of solar power generation by detached house is calculated based on the insulation rate by household type. Average is 4%. The scenario 3 is insulation performance improvement. In this scenario, all Kyomachiya and detached wooden house will rebuild to new insulation standard, and all apartment houses will be rebuilt to the also rebuilt to the new insulation standard. The end of the scenario 4 is to diffuse their energy house. Because the landscape low, Kyomachiya cannot install solar power generation, so Kyomachiya will rebuild to new installation standard, and other wooden house will change to zero energy house, and all apartment house will also rebuild to the new installation apartment installation performance apartment houses. And now is 4 scenarios result. this picture is residential energy consumption by installation standard. We can see that that all simulations settings not change, only change the installation performance. That detached house improves the installation performance to certain extent to reduce the heating and cooling energy consumption. But for apartment house, with the installation performance up, this effect is not obvious. And now is the household energy consumption for this first scenario, and this left picture is energy consumption by use. Installation performance improvement scenario, and just can reduce 8% energy consumption than BAU scenario. And when the zero energy house diffusion and not use PV generation can reduce 15% the energy consumption. And the right picture is energy consumption by energy source. If zero energy house diffusion scenario, or you use solar generation, it can reduce 43% energy consumption. And the end of this result is greenhouse gas emission for each scenario. We can see that improved installation performance can reduce greenhouse gas by 0.21 million tons. And in the zero energy building diffusion scenario, and zero energy housing can reduce greenhouse gas emissions by 0 to 4 million tons if they do not use solar power, and 1.36 million tons if they use solar power. The next is a regional economic effect. We also use IO analysis to check these four scenarios, how it can affect the local economies. The result is when BAU scenario change to zero energy house scenario, it can bring 615 million our economic effect is to Kyoto City. And now is the summary. And we have these five summary. And first is the scenario to improve the insulation of Kyomasia and other houses did not contribute significantly to energy consumption and carbon reduction in Kyoto City. The reduction rate is only 60.9%. And in just improve insulation performance, it can have an impact on local economy of about 73.6, or including the GRP by about 0.1%. But if all scenario change to if all detached house to their energy house would contribute significantly to the reduction of energy consumption in Kyoto City. And this change may be impact the local economy about 658, or including GRP by about 1.3%. And it would be described to consider methods to convert Kyomasia to their energy house while perceiving the traditional landscape of Kyomasia. And this is all my presentation. Thank you very much.
Thank you very much for also for transporting us even visually to Kyoto. So we do realize how difficult it is to combine the energy efficiency gain with traditional housing, which is I mean a huge problem. But still, we don't want to, in the name of energy efficiency, to also to destroy the cultural capital. I was wondering, which is your feeling about the point of view of the regulators or the cities. So in terms of you give us some figures about the I would say cost efficiency of this renovation, but we also understand that the investment is huge. So which is the most likely one according to the current policies? So you think that there is a chance that we're going to move to the scenario 4, or
I think the zero energy house is more better than the reform. Is this your question?
So there are no specific programs to really convert these houses. Not yet, maybe.
Yeah. I mean, maybe this meaning is I'm so sorry. I'm so nervous. So.
No problem.
Okay.
Okay. So we have, in any case, we have the results that are interesting of, I mean, your study, and of course, it's not only a problem of efficiency, but also, as I was saying, to integrating also in the landscape those houses, and so without also making too heavy intervention on them.
So in my opinions, maybe in this research is just make all commercial or detached house to their energy house, but maybe we can search some method to keep the traditional house we really look, and in other hands to improve it and energy efficiency. And this is my opinion.
Yeah, it's interesting. It's interesting because our perception is completely, I mean, outside the system. So it's interesting to have also your own feelings, your own understanding.
Okay.
Thank you very much. It's now time to move to our last speaker, Yolanda Sevinch from the GRC.
Hello, everyone. Let me share the screen. My name is Yolanda Saviuk. I am here to present to you, and I'm very happy to present to you the report that the GRC has published recently on explicit demand response for small end users and independent aggregators, in which we have analyzed the status, the context, and then we looked at the enablers and barriers. I have to say thank you to the organizers for creating such a great panel, because the discussion fits very well with the previous presentations, which were very interesting. Thank you very much. So we are all very familiar here with demand response, but nevertheless, I'm going to quickly set the background. The problem that spurs all of this is the fact that electric grid is, first of all, aging, and second of all, it has not been designed to sustain the newer developments with more renewable energy sources, more active consumers, bidirectional power flow, intermittent generation. So then this puts an additional strain on the grid, which means that the system needs more flexibility. And some of the solution, part of the solution can come from demand side flexibility, in particular demand response, which on the one hand can be cheaper than investments in the transmission or distribution networks, but also has the welcome side effect that once we have demand response in place, we will have the necessary mechanisms to ensure more reliability and more resilience in the grid, in which the grid can react quicker and more nimble to external events. Now, demand response, as also previous colleagues have mentioned, it can be implicit or explicit. Our report focuses on the explicit demand response, where well, implicit demand response is more passive. Here in Europe, we are very familiar with night tariffs and day tariffs, where you can have cheaper electricity at night. So then if it's an unessential load, such as a dishwasher, you can always decide, I'm going to do it at night. Whereas with explicit demand response, users are actively encouraged to shift their consumption. Also, the outcome is the same. You flatten the peak, but it's on a more granular basis. It's more on a when it is needed, a time of need basis, and it's not just any time after midnight, but as a certain hour when the system, the optimized functioning of the system requires it. Now, on the EU level, the Electricity Directive, it formalizes the participation and the role of demand response in the grid, and also foresees and makes room for a third-party entity, which is the independent aggregator, which is to say that, well, the utility companies, the retailers, the power suppliers, they are already in the house of the consumer, no, at the power socket. So they are already in the prime position to harvest all of this consumption data, to pull together more consumers, to participate with an aggregated load in the markets. So they are already there. But the idea is that if the technical requirements are fulfilled and if there is a business case, then member states should ensure that this third party can participate in the markets, because then the idea is that maybe the competition would be different and better balanced. Now, the products with which demand response can participate in the market fall into one of these three categories: either energy that hasn't been consumed, which is not the same as energy saved, energy that hasn't been consumed during peak hours and consumed during more convenient times, which also frees up capacity during peak hours, and of course participates through ancillary services in tertiary markets for frequency reserve and congestion management. And more to the point of independent aggregators, first of all, they compete with utilities, as I was saying before, for winning over customers to aggregate. The problem is that one single household, the consumption amount of one single household does not really make such a big difference on the grid, which is maybe not interesting for the utility to take into consideration. But then maybe 10 households or 50 or 100 households, that's already an aggregated load that makes a bigger impact. And in seeing it on that level, then the energy, the capacity, and the ancillary services from demand response, they can de facto compete with generation, even though today with the prosumers, more active consumers who also have self-storage, maybe with electric vehicles, demand response does not necessarily compete with that kind of generation, but more it's integrated and it optimizes. They are complementary. Now, we at the JRC compiled this report in which in 2021, as you saw on the previous slide, the directive was due to be transposed by the end of 2020. Article 17 deals specifically with independent aggregation of demand response. So we launched a survey in which we addressed national regulatory authorities as well as utility companies, industry representatives, and academic experts in each member state, focusing on small end users, so households, because small end users, first of all, they constitute a large homogeneous group that can be analyzed. And second of all, because small end users, households, are at the center of the energy policy in the EU. So it was interesting to see how is the Article 17 transposed in national legislation and what is the real life reality in the member states, what is the status of independent aggregators as of 2021. So what we found through this survey was that, first of all, compared to the previous report, also carried out by the JRC in 2016, explicit demand response, engagement in explicit demand response has increased consistently across member states. It is available through the suppliers, first of all, to households in 22 member states. Then also independent aggregation, as it is recognized in primary legislation at least, is recognized in 19 member states. Secondary legislation is not always easy to track. So to what degree secondary legislation is full. But 19 member states for at least primary legislation, that was our finding. And in 7 of the countries, we already found independent aggregators that operate, exist, are registered on the market. They address small end users. Now, this is a map of the findings, and it, with different shades of blue, we have illustrated the 3 categories. Now, if you look very well, very close, you will see that in the end, all 26 states are colored and not just 22 as suggested in the previous slide. And this is the reason that there are also some anomalies. Let's say, for example, the case of France, which is the member state with a very solid tradition and know-how with independent aggregation for small end users, where there is a logical sequence of steps where first the explicit demand response becomes available to the users, then more users can get engaged, maybe first through the utilities, then there is a business case for an independent aggregator, and then this becomes a market, is consolidated, and this is the reality. But the problem is that not everywhere the legal framework mirrors the evolution of the market. So then on the other side of the spectrum, we have countries such as, for example, Romania, where there are independent aggregators on the market. The website of the National Regulatory Authority publishes every month a register with participants in this market. It is a growing list of registered independent aggregators. There is at least primary legislation that accommodates independent aggregation and some secondary legislation as well. The problem is that there is not really a lot of explicit demand response available to the population. So that is to say that the laws are there, the market is ready, The participants in the market are already in starting position, but explicit demand response, first of all, the utilities, they don't really have many programs to offer. And second of all, the rollout of smart meters is behind. So this is why there are mismatches across member states. But anomalies aside, there is this logical sequence of steps. First of all, you have to first be able to engage in explicit demand response, and it comes first through your supplier. And then in a second step, when the market is mature, if conditions are fulfilled, now then let's see if it's possible to also engage in independent aggregation. So our report also looked at the reality on the ground and to investigate what are the barriers, what are the enablers, and we disentangled these two steps. So then we found that, first of all, let's see barriers and enablers for explicit demand response. And we found some barriers, of which I would like to, for example, highlight the fact that sometimes if the electricity is so cheap that for the end user, for a household, it is just the savings, the potential to lower the electricity bill is just not enough to be worth it. Because as I was mentioning at the beginning, engagement in explicit demand response takes a little bit of well, more participation, more active participation. It's on a more granular basis. You have to optimize when to switch on, when not. Of course, you can outsource this effort to aggregator, independent or not. But in any case, it has to be worth the effort. If it's not, and if electricity is too cheap in comparison to the income, then that is not worth it, and there is no business case. Now, the enablers for explicit demand response are mirroring a little bit the barriers, because, for example, in countries with very expensive electricity, let's say, for example, Denmark, the potential for financial savings are higher, and so then it becomes more interesting. Now, once the users can at least engage in some form of explicit demand response, then we looked at the market. Let's see, how about independent aggregation? Now, these are more, these barriers and enablers, they can be either legal or business related or technology related. In terms, I would like to highlight here a chain of events, a route for independent aggregators. They would be a very new entity, and like every new entity that tries to enter the market, the road is bumpy and there are hurdles at every step. For example, there is a technical requirement. The technical requirement is a minimum bit, which means that the aggregator needs to collect a large enough load with which to be allowed to participate in the market. But this technical requirement needs a large enough pool of end users to make a business case. But to make a large enough pool of users, first of all, sometimes there are geographic constraints because there are bidding zones in countries such as Sweden or even Italy. There's also in some countries data privacy concerns from end users, and so on and so forth. So the barriers are a little bit at every turn. The enablers, on the other hand, they're not necessarily as much mirroring the same the barriers. I would like to highlight of the enablers that we found the possibility to engage in value stacking, which is to say that this entity that is the independent aggregator, if they can create revenue from more than one stream, more than one value stream, not just to participate on the markets with the demand flexibility, but maybe also add stack on top of this the possibility to use the storage, because maybe the households have electric vehicles, or maybe the possibility for this aggregator, this entity, to act as a virtual power plant through combined generation from users that are prosumers. This already increases the business case and, of course, improves the prospect for entities such as the independent aggregator. So to summarize, in terms of demand response, explicit demand response, our report shows that there has been progress everywhere across the EU, but not equally, not the same to the same degree. And access to explicit demand response that has to be well enabled is usually a prerequisite to engage in to have independent aggregators on the market. And independent aggregators need or require further enablers to fulfill the spirit of the directive of Article 17, of which I would like to also highlight the fact that, yes, this rollout of smart meters is fundamental. Now, of course, there are also exceptions. There are also cases where you don't need to have a smart meter at every household. It's possible to have one smart meter per node or per pool of participants. But this is an exception, and the smart meters will be here at a very high degree rather soon, sooner rather than later. So all the future scenarios are already taking this into consideration. Having 1 meter per X households is a workaround and not something to look into the future with. So in conclusion, yes, there has been progress, but it's not really measured, and it's not, demand response is always a little bit a topic that is not the first one to come to mind, is not as prominent as development of renewable resources, for example. So more measurement and more communication to replicate best practices would help. And in order to achieve that, a bit of quantification of success and the cost-benefit analysis that would, yeah, we look forward to learning more about this. And yeah, this is my presentation. Thank you very much. I'm open to questions.
Thank you very much for this very interesting overview on the implementation of the directive. I was wondering, just for clarification, if you take into account also not only the existence, but also, let's say, the market share of these aggregators, or how many consumers are they are able to embark?
It's a very good question. Thank you. In terms of market share, so first of all, if we only look at aggregators that only address small end users, it is, let's just say, not statistically significant. Because now I should have also maybe clarified, demand response and aggregation of demand response from large users, that's already old history. That has been done for a long time. It's nothing new. This is how the contracts are tailored with large consumers. So aggregation is not a new thing. It's not a mystery. So then the problem is not to aggregate. The problem is if those aggregators who are already on the market accept to take on into their portfolio not just the large users, but also the small users. Only in France, there is, to our knowledge, one company that deals with medium, commercial, and small end users, because their market is so mature, so they can pull more resources. But just specifically for small end users, there is no data for that yet.
The case of France was exactly the one that I was wondering about, because if the aggregator is also the ex-monopolist, which I think so. I mean, I don't know if it is an aggregation. It's a pure model of an aggregator, or there is just the fact that there is not enough switching to others, and therefore this may favor implicitly the role of this aggregator. And I was surprised in your map to see that France was between the blue, the deep blue. So
no,
I
in what we found, there is at least one company with significant portfolio. It is in our report, like also more detailed. Voltalis, you probably are familiar with the name. We analyzed them and we saw, well, yeah, they aggregate small end users. The problem is that in terms of the size of the portfolio, it's difficult to disentangle what of that number is just households or is it the entire portfolio. And when on the side of the regulatory authority, when they publish the tenders for demand response every year or every semester, well, it's this and this many gigawatts, but that is the tender for all demand response, not just for you see small end users. So our approach was to see, okay, is it possible for households to really participate in this, first of all? And second of all, is there a business case? Now, how large the portfolio has to be, that is already depends on the local market, how expensive electricity is, da-da-da.
Thank you very much. I don't know if also the other participants have questions or remarks.
I have a question to Yolanda. I appreciate very much your presentation, and because the idea is that we have to aggregate final user. We have to invite them to participate also in the demand response program, etc., etc. What do you think? Maybe a regulatory modification that can improve and your approach and can involve more and more people in the program, if there is any.
Well, generally on a blanket, as a blanket for the EU level, what our report found was actually that for once, the regulatory framework, because we saw also what were the most cited barriers in the previous report. So in comparison with the previous report, for once, we saw that, well, the regulatory framework is not cited as their first problem. Or in countries such as, let's say, for example, Spain or even in Italy, it is possible already for independent aggregators to start doing something. The problems that they cite are more to do with the secondary legislation, because maybe the compensation mechanisms are not clarified yet. And this is up to each member state to figure out and to decide. That's one thing. And yeah, the market barriers, the minimum bid, let's say, for example, in the Netherlands, there's they have their complaints there with that the minimum bid is too high, or that the balancing responsible party has requirements for balancing the responsibility, the symmetrical bids, those are way too high. So those are, yeah, parts of the secondary legislation which are specific to each country.
Thank you.
Thank you very much, the four of you, for these very complete sessions that comes across case studies, but also some policy questions and modeling questions. So thank you for the organization, and I give the floor to the organizers to end that session.
Thank you all for your interesting presentation and for participating. Have a nice day, everyone.
Thank you so much.
Bye.
Have a nice day.
Bye-bye. Thank you, everybody.
Thank you so much.
Bye-bye.
Bye.
Bye-bye.